Hey folks, welcome back to the unit on similarity. We're going to wrap up video number 3 for proving triangles similar. So in the previous 2 videos, we talked about the angle-angle postulate, we talked about verifying triangle similarity, and we even proved some triangles similar. We learned 2 other postulates as well, side-angle-side similarity and side-side-side similarity. So in this lesson, we're going to talk about finding lengths in similar triangles. So it's what we would call real-world examples. But I'll go over a couple of examples from the book, and then we'll finish with a quick quiz. So we're going to find lengths now in similar triangles. How is that going to work? Well, let's take a look at this example. We're going to talk about rock climbing. Whee! So before rock climbing, Darius wants to know how high he will climb. Isn't that a helpful thing to know? He places a mirror on the ground and walks backward until he sees the top of the cliff in the mirror. Okay, so understand what's happening. Dude puts a mirror on the ground and then walks backwards until he can see the top of the cliff in the mirror. What's the height of the cliff? Now, we don't need the picture, but there is a picture. We don't need it because hopefully you can see what's happening. So we have a mirror lying flat on the ground. The importance of lying flat is that we can have these 2 bases on the same plane, making a linear pair. That's important because we need to establish right angles. Because Darius stands and the cliff is right north from the ground. So how in the world are we going to figure this out? So remember what's happening. Not Cliff. That'd be funny if instead of that his name was Cliff. That'd be funny. Anyway, so Darius knows how high he is. Darius is 5 foot 5 inches, right? That's how tall he is. And Darius is standing 6 feet from the mirror. When he walks backward, he walks 6 feet backward. So we have something happening. We have proportionality with Darius, his height, and the distance from the mirror. Now, how do we know this is proportionality? Because what's interesting about this? Darius is standing straight, so he has a right angle. Okay? The cliff is straight up, so we have a right angle as well. Now, how do we know we are dealing with similar triangles in this case? Well, because vision, the way it works, and reflecting off of a mirror establishes congruent angles. Congruent angles. Because, why? Because they are supplementary to the same angle. Okay, so they are congruent to each other because they're supplementary to the same angle. So we have congruent angles. And if that's the case, guess what? We have angle-angle similarity. Okay, so what we are working with is angle-angle similarity because we have the 90-degree angle plus the vision reflection piece. Okay, and that's the importance, again, of making sure the mirror is flat. With a flat mirror, we can establish angle-angle similarity because we'd have the 90-degree angle from straight up and the congruent angles from the line of sight. So we have proportionality then. So we have Darius being 5 foot 5 or 5.5 feet. It's actually 5 foot 6, and then the distance from him to the mirror is 6 feet tall. So what is happening? Well, that's going to be equal to, because it's proportional to, the ratio of the height of the cliff compared to how far the cliff is from the mirror, which in this case is 34 feet. Now, how do we know it's 34 feet from the cliff to the mirror? You can measure that stuff. Okay, so if you know how far you are from the mirror, you can also tell how far the mirror is from the base of the cliff, right? So you have your proportionality. Now, you can also make other proportions. Okay, there's all sorts of things that we can do here. What if we looked at our congruent triangles and we set it up with corresponding sides? We could say that 6 to 34 would be equal to 5.5 to x. And then guess what that brings us to from our first lesson when we did the first lesson on equivalent proportions. This is also the same. No matter what, the product of the extremes, well, that's the means, by the way. The product of the extremes is equal to the product of the means. Okay, so when we look at the extremes in this example, the extremes would be 5.5 times 34. Okay, so just got to do a quick calculation. I don't know why I'm not doing this in my head, and I feel guilty for not doing it in my head, but every time I look at a decimal, I'm like, oh, I need a calculator. I don't know why I do that. I shouldn't. Anyway, 5.5 times 34 gives us a number. Yeah, 187. Okay. So no matter what, we're going to have the product of the means is equal to the product of the extremes. In this case, the product of the extremes, 6x, is equal to the product of the means, 187. No matter what, we're going to have the same equation. And so when we divide both sides by 6, we have 31.16 repeating. Okay, so that's going to be our missing value no matter what. Okay, so what does that mean? That means the cliff height is about 31 feet. Okay, so what's the height of the cliff? About 31 feet. So Darius is going to have to go up about 31 feet. Okay, so that's how that works. Yay! Similar triangles with a mirror. Let's do another example, shall we? No, Mr. Katz, I'm done. I get it. Oh, I so get it. All right, well, what if I don't draw you a picture? Do you get it then? I didn't think so. All right. A flagpole casts a shadow that's 18 feet long. At the same time, Rachel casts a shadow that is 4 feet long. Rachel's 5 feet tall. How tall is the flagpole? Rachel is 5 feet tall. What's the height of the flagpole? So what is going on? Draw a picture. Here's a flagpole. Flag. Here, I'll even do like a little bit stars and stripes. Okay, so there's our flagpole. And it casts a shadow that is 18 feet long. At the same time, now that's important. This is the key, at the same time. So at the same time of day, everybody's shadow is the same proportion, by the way. At the same time, Rachel casts a shadow. Here's Rachel. How do you like her hair? Anyway, Rachel casts a shadow that is 4 feet long. Okay? But how tall is Rachel? Rachel's 5 feet tall. Okay, so Rachel's 5 feet tall. And what's the height of the flagpole? So that's the question now. What do we have here? If it's at the same time, the distance from boom, 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 and boom, 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 because of the shadow, right? It's at the same time. We know that these angles are congruent because at the same time, it's the light is hitting the ground at the same angle, right? Or light is being intercepted at the same angle. And since we're talking about tall, we have right angles. And since we have two congruent angles, we have angle-angle similarity. We know we are dealing with similar triangles. So now we have our proportions. And like I did in the previous example, it doesn't matter how we set it up. We can say that Rachel being 5 feet to 4 feet would mean the flagpole's height to the shadow's length. We could have that proportion. Or we could use corresponding sides, right? 5 feet to the length would be equal to 4 feet to 18 feet. Either way, when we establish the product of the means is equal to the product of the extremes, we're going to end up with the same equation, which is 4x equaling 90. Hey, I did something in my head finally. So 4x would equal 90 because 5 times 18 is 90. So when we divide both sides by 4, we have 22.5. Again, I got to use my head on that. Hopefully that's correct. So what's the height of the flagpole? 22.5 feet. Now the other thing you should be careful in problems like this is if we went ahead and switched up units of measure, right? 4 feet, maybe I did inches or meters or whatever. But you got to be careful with that stuff. So that's it for finding lengths. Let's do a quick quiz and we'll call it a unit, call it a lesson. So I'm going to do this pretty quick. All right, as fast as I can answer it. Are KRA and FLN similar? If yes, explain. So here's one triangle, there's another triangle. The sides are congruent. The sides are congruent. That means it's isosceles triangle. Isosceles triangle, which means L and A are congruent. Both are 71, by the way, because it's isosceles. So yeah, they're totally congruent. Why are they congruent? By the angle-angle postulate. Because 71 is congruent to itself. We can't say side angle side because this isn't side angle side. We didn't talk about K or F. And we can't say side 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 because we didn't establish proportionality at all. So angle angle indeed. Okay, so notice how we have a tricky question like that. Next question. Are the triangles similar? If so, what's the similarity statement? So I did this before, I'll do it again quick. Longest, second longest, third longest. Longest, second longest, third longest. So 4.5 corresponds to 15. Is that going to be equal to 3.3 corresponding to 11? And is that going to be equal to 1.5 corresponding to 5? Okay, so how do we figure all this out? Now, we could simplify each fraction, or we could divide, right? 4.5 divided by 15 is equal to 0.3. So this is 1/3. And 3.3 divided by 11 is 0.3. So it's kind of like, it's not 1/3. It's not 1/3. I shouldn't have said that. And 1.5 divided by 5. Is that 0.3? Yes, it is. Okay? So it's 3/10, by the way. 3/10, silly goose. So all these are the same. And if these are the same, these are proportional. So the answer is yes. But which triangle is which? Ha! Now, how does this work? Notice how triangle, first one, we'll call it DEF. Let's say triangle DEF. What would that correspond to? What would that be similar to? So D and E is on the other side of the second, let's say angle D is between the third and second angle. So between the third and second angle is angle W. Okay, so we have triangle W. And then between the first and third angle, we have F. So between the first and third angle, we have X. That would be the last one, which leaves Y in the middle. So DEF is similar to WYX. So DEF, WYX, check. Or we could have said DFE to WXY. No. Or we could have said DEF to WYX. No. Okay, so notice we got to be careful with similarity. That's a tricky question. All right, so correspondence counts. Folks, I'm out. I hope you have learned some stuff about proving triangles similar. That's it for this lesson. We'll continue on similarity later with right triangles. See you later.